Hello, uh, this is Rahil Aman Memon, Dr. Rahil Memon, and we are going to start the remaining part of our course operating systems from today, and we hope to conclude this operating system course in online in online sessions. So, as you might have already received the email from my side, also from the administration side, and the Sakar IV has taken a good initiative to not hold on the learning process due to this pandemic situation. And I personally believe that this opportunity is really a good opportunity for you guys also. This initiative is also a good opportunity for you guys to start a new way to the learning process. So we were already in chapter 4, I believe, but as it's been long, maybe more than 2 months, so I think that most of you guys might have the one group, maybe A or B, was in the mid of chapter 4, and another group has not yet started the chapter 4. So I decided to recover the chapter 4 from very first, so that we all remain on the same page, and also the group A and group B students are merged into this in one group here in the LMS. Okay, so we are going to start threads and concurrency. As we have already studied about the processes, we know that a process is actually a unit of work. We say that a process, if we see here, a process is basically a unit of work, right? Whereas the thread is a unit of CPU utilization. Now, the main difference between process and CPU and the thread is that a process is actually a complete task, a complete work which should be done, and a thread is a subsection of the work. The simplest definition of a thread is that a process is divided into multiple threads so that it can it can be performed faster, right? Also, the resources and resources like memory, like processing, is efficiently utilized here. Okay, this is faster and this is efficient. Okay, so we'll see the overview. We'll come to the overview. We'll see that what is a thread and how the threads are formed, what are the components of threads, and then what are the applications of thread, and also we'll see some examples. Then we'll come to the multi-core programming, where we will see that actually the traditional programming, which is single thread programming, is different than the multi-core programming. Okay, because in single core we just write code which goes into a single process and it executes over there, while when it comes to the multi-core programming, when you have maybe one task which should be given away to several cores, or maybe several threads are generated for this process. So the multi-thread process is different than normal program. Okay, so we'll see how the multi-core programming actually works, what are the techniques, and then we come to the multi-thread modeling, that what are the type of multi-thread models. Actually, there are two type of threads: the user thread and the kernel thread. User thread and the kernel thread. So we will see that what is the difference between user thread and the kernel thread, and we will also study different models which operate for these two type of threads. and then we will see what are the libraries, the application interfaces, right, APIs, which facilitate these threads to occur in any program. And then we will see that implicit threading, actually threading and managing is a difficult task actually, and to create a thread, new thread, when to create a new thread, how to create a new thread, and how to manage these threads is very tricky part of implementation of threads. So we'll see that how the threads, implicit threading actually work, and then we will see some of the threading issues, how these can be resolved, and then we in the end we will see this chapter, and this chapter, that how what are the examples of multiple threadings in current in the most modern operating systems like Windows, like Macintosh, Linux, and Unix systems. So this is a course overview, and so the objective of the course and the motivation. So most modern operating systems implement the multi-threading concepts. Multi-threading is implemented because we have now currently more than one course in a system. Traditionally we were having single core operating system, single core hardware systems, where we have single CPU and we have single process which goes, and for the concurrency means simultaneously execution of multiple processes is achieved by the time shared systems, as we seen in the processes that we might have. Just a second. That we might have a process, maybe more than two processes, P1, maybe P2, maybe, right, P2 maybe, and then we again have P1 and P2. These are actually time shared system. So we, for each portion of the process, or for each process, we have some specific time to execute. This is this is done by a scheduler, where we can execute, we can exhibit that execution of multiple processes is concurrent, okay, on the same time, but actually this is scheduling, right? In the multi-thread systems, the concept is different, because we have one process, and this process can execute in really multiple in really concurrent way, right? Parallel, the word, instead of using concurrent, we will use here parallel, because the execution of the system of the processes is done in the parallel, where P1 and P2 are executed in the parallel. But so this parallel concept also applies on the threads, because as I have already told you, that a thread might have multiple a process might have multiple threads here, right? Multiple threads are generated, and when these multiple threads might go to multiple cores of a system, okay? So this is again a parallel concept, a parallelism concept, okay? So most modern operating systems are multi-threaded operating systems, and threads, whereas a thread actually belongs to a single application. Maybe if we have a web browser, right? Web browser or etc, or maybe we have MS Word, or maybe whatever the programs we have. But for a single application, we can have multiple threads. For suppose for this application we might have multiple threads, for this application we might have different set of multiple threads here. So the multiple tasks within an application can be implemented by separate threads, and some of examples of these are update display. For example, when we copy or paste the images, okay, then there is also thumbnails created for that image, okay. Then you delete or update or add some new images, again the thumbnails are updated, Okay, so this is also an example of multiple threads. When you see the thumbnails, these thumbnails are actually example of multiple threads. Fetch data, for example, if you see the web browser, right? Web browser here, if we see the web browser here, then a web browser is a multi-thread, because when you request a page, then this page might have image, text, right, or maybe some other data which should be fetched, and each fetch of data is actually a one thread, maybe T1, T2, T3, right? And also spell check in MS Word. If we go to the MS Word example, then spell checking, word count, right, and maybe keystrokes are different threads in MS Word, which belongs to this application of MS Word. And answer to a request, maybe if you see the client server architecture, then each request you make from the server is actually resolved by server as a thread. It is received by one thread, it is executed by another thread and replied back to the client. So these are very popular examples of multi-threading. Furthermore, if we see that efficiency of multi-thread can we can say that most really a good example, the really where we need efficiency for in the applications like data mining, or maybe a sorting algorithm, right? Sorting algorithm, or maybe a graphics, right? These all applications can also get a good benefit from the multi-threading examples, right? Multi-threading programming, multi-thread programming, and process creation. Actually, why this is a good concept to implement, because a process is a heavyweight process. A process is a heavyweight task, right? While a thread is a lightweight task. So we say that a thread is a lightweight task, while a process is a heavyweight task. Okay, and because whenever we create a process, we have to allocate resources like memory, okay, and like maybe some stakes, or maybe some processing specifically to that process. These are actually resources which are specifically required for a single process, while a thread is a lightweight process because it requires a subsection of a subpart of these resources from the main process. So it does not require to reallocate the resources, but it utilizes some part of the existing resources in the in a process, in a full weight process. Okay, so furthermore it can simplify the code and also increase the efficiency. And nowadays the kernels which are actually underlying of our operating system, the underlying engine of our operating system, are mostly multi-threaded. And we'll see that we have different type of kernels, different type of threads, which I have already told you that we have user thread and kernel thread. So we have threads on actually application level, and we have also threads on the kernel level. And okay, so what is the concept? So actually there are different components of a thread, and we can say that a thread can have different components, like components of thread. So we have thread ID, and registers, stake, and program counter as a specific components of the thread, while we have some shared components also, where we have code, data, and files are as a shared. These are shared resources, and these are specific resources. Okay, so we can see that here we have single thread processes and we have multi-thread processes. A single thread process has might have a thread ID. Let's say this is a thread ID, and thread ID is specific to this thread, and we have also register, program counter, stake, and we have code, data, and files here. While in multi-thread programming we have a thread ID, maybe let's say T1, T2, and T3. Okay, so this is a thread ID, and a program counter, stake, and register. So these components, these four components are specific to a thread. If you create a thread, then you have to have these components specifically allocated for the thread. And while so we can say that there are three threads, and each thread has specific components to which belongs to itself only, while we have also some shared resources. Right? So we have some shared resources like code, data, and files. This is a multi-thread model, and this is a single thread model. So I hope that you now understand that what is a thread and what are its models, and how the threads actually are represented inside an operating system. And so further we move to the example of the multi-thread in client-server architecture. Okay, just wait a while. Okay, so we'll see here a multiple request coming from the client to a server. Let me select the pane. So now we have a client here, and we have a server here. Maybe we can say that the sole portion actually belongs to a server, and this is client, right? So now in the server side we have two threads. Thread one, which is one is the server thread, and another is we have actually two threads. The one is listening thread, another is the thread specific created for the process. Okay, so if we redraw this picture for better understanding, so we have a client here. Okay, this client, maybe we might have multiple clients. Okay, C1 to Cn. Okay, C1 to Cn. So these clients actually send request to the server, where server have two threads. One thread is for listening, and another thread, maybe multiple threads are here, which are, maybe we can say that T1, T2, and T3. These threads are another type of threads, maybe image rendering, maybe text, and maybe some other data, maybe videos, right? So when this thread is actually all the time listening to the incoming requests, and once it receive a request from here, it actually creates a new thread, and allocate the resources, allocate the resources of server to that for that process, and in response, and some response is thrown back to the clients for that thread. Once this thread is once the thread has finished its work, then it is actually it is actually put back into a pool of threads. So we'll see later on what is the thread pool. So for now, you understand that this is a thread pool, and whenever some work related to that thread comes up, the request arrives to the server, then server allocates a new take the thread from the pool and allocate the required resources to that thread, and the task is done. Once the task is done and the resources are freed up, and the thread is pushed back into the thread pool. So this is normally as client server architecture of working of threads. Okay, multi-thread. Okay, so we have seen that how threads are actually working. When server accepts requests, the server actually in real time, the server receive requests from thousands of clients. So serving those clients concurrently is not possible. Traditionally, this is done by maybe like multiprocessing, as I have already told you that each incoming request creates a new process, and that process is sent to the for the processing to the CPU, and then CPU performs some tasks using the scheduling algorithms, different scheduling algorithms on priority or maybe some other basis. And then once the task, once the process is the allocated, the process is free up the allocated resources and reply back to the clients for their request, then only new process can come. So using those approaches, the time over the server was very large, and however the use of multi-thread has reduced that time to very minimum. And now we can see that even if you want to access your photo which was uploaded on Facebook maybe 5 years ago, you can still get that photo back display to your display within a very short time, maybe only some microseconds or maybe seconds if you have a good internet connectivity. So this is actually the magic of multi-thread in the operating systems. What are the benefits of this? So the benefits, the most we can say that very efficiency is most required, and responsiveness is mostly required from the such systems where you have different type of clients, and everybody has to fulfill its request very earlier. So in using threads, you can actually achieve that goal. The responsiveness is much more desired in this type of applications, and threads is insert to that type of application. This may allow to execute a part of a process while the other part of process is actually blocked. For example, if we see that we have some process here, right? Maybe, and then maybe if we say task, I think it's okay. If we have a task here, and we created some threads T1, T2, and T3. Now, even if this part of program is blocked, still the other parts are working. So we don't encounter the blocking in the multi-thread system. Okay. Furthermore, the resource sharing, as I have already told you, that there are several components of a thread, and several resources are also in which we have some resources like code, like data, and like files, which are the main resources of a process, of a thread, are shared among the multiple threads. So instead of for example, if we go to the processes, then we have different approaches, like we have message passing, we have shared memory space. So those are actually good approaches, but still time consuming approaches, still processing and process hungry approaches. But trade is not that much hungry. It actually shares a part of the resources from its parent, right? Okay, so that's why resource sharing is also one key benefit. So the first one is responsiveness, second one is resource sharing, and third one is economy. Now if we have for suppose in processes, if we have something like context switching, right? Where we have PCB, process control block, and it stores some context of a process, and whenever we switch to another process, the new context is actually retrieved. So we have multiple program counters, process control blocks, and we have also we use those program control blocks for the context switching. From one process to another process, we have this approach of context switching, and we have seen that for switching from one process to another process, we have some time which is actually wasted. Here, but in this approach, this is a very lightweight process. As we know, the thread is very lightweight process, so context switching is not that much overhead here. Is no overhead, right? Or maybe minimal overhead of the context switching. So cheaper than process creation, thread switching, lower overhead than context switching, right? So low or maybe no overhead of the context switching. So this is an economical approach. Also the scalability in terms of, if you have a multi-core process, with multi-threading, then such system is very much scalable, right? You can take a full advantage of the multi-cores and implement multiple threads where multiple processes can undergo the processing concurrently and in parallel. So the scalability of this is also one of the major benefit of this approach. So furthermore, we move on to the multi-core programming. In the multi-core programming, the earlier approaches, instead of the single CPU, multiple CPUs were physically installed on the system. Since we have previously we were having single CPU, then a new era came where people have started to install multiple CPUs over one system to enhance the performance of a system, or maybe to implement the multiple processing in one system, using one entire resources. The other hardware resources were used only single, while the processes there were multiple processors installed over that system. So to overcome that process, we came up with the multiple cores, where now in previously we were having multiple CPUs, maybe CPU 1, CPU 2, and CPU 3. This is a very previous. Before that, we had only one CPU. this is maybe we can say the one generation, this is two generation, and third generation is that we have a single CPU with multiple cores. So we say core 1, core 2, core 3, maybe core 4, right? So let's come to the standards. We have 4 cores. Okay, so we have 4 cores in this system. This is might be we can say that for the processing this is a third generation. Now currently we have mostly systems like this, where we have multi-core processors in our systems, and this approach has very good outcome for the scalability and for the performance, but it has also some burden over the programmers. The burden is to resolve some of the challenges of the programming, like dividing activities, like balancing, like data splitting, then data dependency and testing. Now we'll come these 5 challenges one by one. That what is dividing activities. Now if you have one task, then how you divide that task, right? Let's say this is task 1, and let's say T1 and T2. Okay, now how you divide this task into 2 threads, that each task has equal work to perform, right? Requires equal work to perform, because if it goes to 2 different processors, then one might be consuming more time and one might be consuming less time. Then this is not the way. We have to do a fair policy here, that both the tasks, or maybe all the activities required, are broken into threads, should have a fair distribution. Okay, these task dividing should have a fair distribution, and furthermore balancing. Now as I have already told you, that balance is also that the tasks should be actually divided in a way that they should balance in some terms, that let's say data sharing and other resource sharing should be balanced also, and also data splitting. For example, if you have one data, let's say this is data, and you have multiple tasks to perform, maybe this task and this task, this thread 1 and thread 2 are going to fetch this data, then how this data should be accessed, or if this data is splitted into 2, then how it should be splitted, because there are 2 conditions. That one condition is that that dependency, which is actually addressed here, that dependency. Now for suppose if one part of data is allocated to this thread and another part is allocated to this thread, then if these are dependent, then they should be synchronized. Okay, and then we have also testing and debugging. The testing and debugging is actually more complicated. Testing and debugging is more complicated in the multi-thread programming, because in the single core thread we have single process and single path of execution, while in multiple thread programming we have multiple path of execution. So in multi-core programming, the testing and debugging, multi-core and multi-thread programming, the testing and debugging is much more complicated, because it has multiple paths for execution. So as I have already, and furthermore I have already told you about the parallelism and concurrency. We will see one example of parallelism and concurrency here. That for suppose if we have a process which is, we say that is a thread maybe is operating on a single core system, then it has, I'm sorry, this might be annoying that I have to select the pane every time, but it's okay. I think it can be adjusted, it can be absorbed. Okay, so this is thread 1, this is thread 2, thread 3, and thread 4, then again thread 1, thread 2, thread 3, thread 4, and then again thread 1, and so on, right? So this is a single core process where we have scheduling approach. Right, and we have a time shared system. Where one thread is executed for a specific time, and for another time we have another thread, and another time we have another thread, and then another thread, right? And then again this thread which were left over here is again resumed here, right? And then the remaining threads are resumed over here, and again so on. This goes like this. And furthermore, in parallelism we might have multi-core operating systems, or multi-core processors. So in multi-core processors we have multiple processes running concurrently on running in parallel over the two cores. So on the same time, we can see that if this time maybe here we have 4 and we have 8, right? Maybe time unit is 8 here, then this can be then maybe 4 or 5. This should be achieved in time unit of the 4, right? So if this take 8 seconds to complete, then this using the multi-cores we can complete this using 4 seconds. So this is the main difference between concurrency and parallelism, where the multi-core systems are desired for the fast processing and efficient resource utilization. So furthermore, the data parallelism and the task parallelism. Actually, there are two types of parallelisms: the data parallelism and the task parallelism. For the data, the distribution of we can say that data is actually distribution of a subset of the same data across multiple cores, and performing some operation on each core, right? Maybe single core you have seen, and the dual core system you have also seen the example in previous slides. We have seen there are two different systems represented here. For example, if we see some programming example, that for example if we have a single core system, I'm talking about the data parallelism now. So if we have a single core system, now we have an array of size maybe n, right? Array of n size, and each element of array should be multiplied, should be sum with itself, right? So these are maybe the element. I'm considering there's a for loop, right, where I is incrementing. Okay, so each element of this array is required to add with the other element of this array, right? So now if we have a single system, then we can say that this array will go with like this: 0 to n minus 1. This is array length. Right? While in multi-core system, this is different. We start this array with 0 and it will go by n by 2 minus 1, right? This is maybe we can say that this is core 1, and the new core n by 2 we go by 2 n minus 1. This is core 2. So these two core divide the data, distribute the some set of data, and perform the same task on different set of data. Okay, this is data parallelism, where you have same data and you perform the part of processing the processing over some part of the data. While in the task parallelism, you have same data, and same data might need to be performed for required to have the different tasks to perform on it. Maybe we can say that let me clear this all. I don't know how to clear. Okay, this is clear. For task parallelism, we have a single task. Let's say this is core 1. I'm sorry. This is core 1, and we have 0 to n minus 1, and we might be performing summation task here, right? And on core 2 we have 0 to n minus 1, and we might be performing multiplication task here. Okay, so this is a task parallelism, or previously we were having data parallelism. So I hope that you understand these two main concepts in multi-core programming, that we have different type of parallelism: the task parallelism and the data parallelism. Task parallelism is when you have multiple tasks to be performed, and in data parallelism you have the part of data to perform the same sort of task. Okay, and here this is also the same thing is illustrated here. You have data, which is part of the data goes to core 1, part of data go to core 2, core 3, and core 4. While in this, that you have different type of tasks. Maybe here you have plus, you have addition, and here you have to add, you have to subtract, you have to divide, you have to multiply. Maybe different tasks. I'm just an example, right? So we might have multiple tasks to be performed here, right? And here we have same task. Everybody is performing the same task here. Maybe addition, right? Summation task. So these two are different concepts you should understand while implementing the multi-threading. That what you have to do, you have to perform the task, or you have to perform the data parallelism. Furthermore, the Amdahl's law. Now, what happens if your data grows? If your data keep on growing, and if you have a task to perform, maybe an application which is running, which is required to be run 25% in serial and 75% in parallel. Now, how many cores maximum you need to get the optimum efficiency? So there's an Amdahl's law which is very much helpful to illustrate this concept. Okay, so in Amdahl's law you have I don't know how we can I don't know if we can have some whiteboard over here or not. But let's see if we can solve some example over here. Now let's take this example. Okay, so here's a formula to calculate that how the how much optimum number of cores you need for an sufficiently efficient execution of the program. So for example, if you have 75% of application required to run in maybe parallel, while 25% is required to run in serial, then how you will calculate it? So for example, if this S is actually serial portion of the program, right, and this N is number of cores. Now if we have 1 by, maybe we need 25% as serial and 1 minus 25 divided by 2 cores, let's see, then how much we need. Okay, so we can see that this is actually 1 by 0.25 plus if we calculate this, then it is 0.375. So this is actually 1 by 0.625 and this is 1.6. so speed up would be 160%, right? If we have single core, which means 1 by 1, then if we can execute for 100% in using single core, then the speed up would be 160% here. And if we increase furthermore, this is when we have 2 cores. If we have 2 cores, then it will execute like that. If we have 4 cores, then again, if we have 4 cores, then it is speed up by 2.2857, right? And if we have, this is what when we have 4 cores. When we have 8 cores, then it is actually increased by 2.666. okay, this is speed up if we have 8 cores. Now if we have infinite number of cores, then what will happen? If we have infinite number of cores, then speed up would be maximum 4. So we have seen that increasing number of cores up to some level is appropriate, is optimum, and increasing number more than that optimum value is useless. And here is the n. As n approaches to infinity, means number of cores approaches to infinity, the speed up approaches to 1 by the serial portion of the program, okay, the S. So you can see that it approaches to 4, right? So up to some parts, up to some portion, we can increase the efficiency of program, but after that we cannot increase the efficiency because the limitations of the serial and parallel portions. So this is Amdahl's law. As long as you increase with the cores, as long as you increase the cores, we can see that this is done well. But ideally we think that it goes like that, but it does not go like that. It does not go like that ever. It goes like at some sort it goes to straight. So now coming to another topic, we have a different type of threads, okay, and we have user threads and also the kernel threads, okay. So we have user threads and the kernel threads. So in the just a minute later, I'm seeing if something is left. Well, okay, let's move on. So we have multiple threads, type of threads. We have user threads and the kernel threads. There are user threads managed and run by user level libraries, and there are three main libraries: POSIX, pthreads. It is actually implemented or used to implement the threads on Unix, Linux, and Mac operating system, while the Windows threads are only used to operate the Windows type of threads. And furthermore, the Java threads, these are we know that Java has Java virtual machine. Java virtual machine means that it has if we have underlying system of maybe Mac, then JVM will facilitate the operating system for the instruction set to be read by the Mac operating system. But if we have JVM here and we have underlying operating system Windows, then it will facilitate the Windows instruction set. So we can say that JVM is actually a facilitator, which is, if it is executed over the Windows, then it will access this API. If it is executed over the Linux, Mac, or some other operating systems, then it will execute these threads. So JVM is actually a facilitator, but we'll call it as a Java thread. Okay, Java thread. Now these threads are actually different type, maybe if I suppose this POSIX thread has both versions, user level, user and kernel, and this is only kernel thread, and this is we know that this is a facilitator, so it can run for the both user and the kernel. So this is the user, this we can create user level thread also, we can create the kernel level thread also using pthreads, while the Windows threads can be only used to implement the kernel level threads, while this Java threads can be implement both the user and the kernel, and for both operating systems, Java, Windows, and the Mac, Linux, and Unix operating systems. So kernel threads are only supported by user. For example, if we have a system here, then we have a user level here, we have a kernel level here. Now we can have threads, multiple threads here for the user, and we can have multiple threads for the kernel here. Okay, and nowadays almost all operating systems, general purpose operating system, has both type of threads, user and the kernel threads. Now, as I already told you, that we have threads here, user level and the user space and the kernel level threads. Now there are different type of threads: many to many, many to one, one to one, and many to one. So this is a many to one, where we have multiple threads created from the user level, and while only we have one kernel level thread which is dealing with that type of with that application, maybe application specific, right? AP specific thread. This is maybe one application, right, which is creating multiple threads. But if but it is creating multiple threads, and this application has only one specific thread in the kernel level. So the drawback of this is that if one user level thread is blocking, then whole the system would be blocking. So blocking is a big issue in this type of threads. If one thread blocking, cause all other to block. Okay, and this is multiple thread this is not the parallel, but it is concurrent approach. Okay, and there are here are the examples of these and this type of threads. Then we have one-to-one. Now this is very ideal situation. This is very ideal, where we have one thread for one kernel thread, one user level thread for one kernel level thread. Okay, but this is actually resource wastage. A lot of resources are wasted here, because for every thread you are creating a new kernel level thread, and this might be time consuming also. And the example of this type of threads are available in Windows and Linux, both operating systems. Another most efficient type is many to many. Means we might have 1, 2, 3 and 4 threads coming from the user level, while in the kernel level we have 1, 2 and 3. Not exactly the same number, but some number of threads are available here to deal with this set of threads. Okay, so this is non-blocking. However, the one-to-one was also non-blocking. But it wastes the resources. Okay, resources. This is non-blocking and does not waste the resources. Okay, and we have also some hybrid level, and this is the fourth type of the threads. Where in the previous slide we had mentioned only 3 type of threads, but this is 4th type of threads. We have combination of threads, right? We have multi-level thread, many to many thread and one-to-one thread. So both efficient are utilized for one application. This is combination, right? Many to many and one-to-one. Many to many and one-to-one. Both are combined. So for implementing these threads, we have thread libraries. The thread libraries are programmed with API for creating and managing the threads. There are different thread libraries. For user level thread and the kernel level threads, we can say that libraries entirely in the user space with no kernel support are available in the user space, and where code and data structure existing in the user space invoking functions results in the function calls. Example, let's go here. Libraries, we have 2 type of libraries. If we say libraries, thread libraries, right? Thread libraries. Then we have 2 type of libraries again, as we know, user and kernel level libraries, right? Here we have code and data. Both exist in user space. Okay, both exist in user space. Also, the function invoking of the function basically result in a function call. While on the kernel level libraries, we have libraries supported by directly operating system, where code and data structure exist in the kernel space. So we have code and data exist in the kernel space. Okay, and invoking a function on kernel level basically results in a system call. Now here we have function call in the user space, we have function call in the kernel level, we have system call, and in the user space we have the code and data exist in the user space, while here the code and data exist in the kernel space. So these are the main differences here, thread libraries. Now we have different type of thread libraries, as we have seen that pthread, and we have also Windows, and we have also the kernel threads.